Hello students, we shall continue with the third unit, that is periodic classification of element or classification of elements and periodicity of it. In the previous video, we had discussed some concepts related to general introduction of periodic table and few concepts related to the nomenclature of the elements which has atomic number greater than 100. Yes, so we will have a brief introduction of this periodic table today. So before moving to this, let me tell you what is, how do you define a shell? Shell means, we say the main energy level is called as shell. The subshells are also called as, within the shells, the subshells, these are also called as orbitals. And you know what is electronic configuration? That is the way of explaining the entry of electrons in various orbitals are called as, or is called as, electronic configuration. So we shall study about the classification of periodic table in detail. In the previous video I had told you that the periodic table, the modern periodic table which is proposed by Moseley, is classified as S block element, here P block element, D block element and F block elements. Please go on making a point of it as I explain. So first we have S block element, that is group 1 and group 2. Let me explain you about it. Few important points related to that. Under S block elements, what you need to understand is S block elements comprises of two groups. Which are the groups? I had told you these vertical columns are called as groups and horizontal rows are called as periods. Now here group 1 and group 2 comes under, group 1 and 2 comes under S block elements. Yes. Group 1 elements are also called as alkali metals and group 2 metals are called as alkaline earth metals. You can see hydrogen. Hydrogen, however, the place of hydrogen is not decided. However, because it shows resemblance with group 1 as well as it shows some common properties with group 17. Just for the sake of convenience, we have just placed it here. Moseley has placed it just there. Apart from that, say lithium, sodium, potassium, rubidium, cesium, francium. This belongs to alkali metals. Whereas group 2 is called as, what is group 1 called as? Group 1 is called as alkali metals. That is, the elements are called as alkali metals. Group 2 metals are called as alkaline earth metals. Earth metals. Yes, which are the metals under this? Beryllium, magnesium, calcium, strontium, barium and radium. And remember the outer electronic configuration of this. Now you have written electronic configuration, isn't it? For different elements you have written. If you observe for these group 1 and group 2 elements, then you can see that the outer shell electronic configuration, I'm quoting outer shell electronic configuration, will be NS1 to 2. NS means N represents what? Principal shell. S means the last electron is entering S shell, and that is why we call these as S block elements. If the last shell electrons P orbital, we call them as P block elements. If the last shell enters the D shell, we call it as D block elements, and so same as that of for F block elements. If the electrons, valence electrons enter F shell. So now coming back to the point, the outer shell electronic configuration is NS1 to 2. For alkali metals, outside electronic configuration, all NS1 you can see. NS can be C. In the case of lithium, 2S1. Next 3S1, 4S1, 5S1, 6S1, 7S1, like that. In alkaline earth metals, you can see the outer electronic configuration as NS2. See here 2s2, 3s2, 4s2, 5s2, 6s2, and you write the electronic configuration. Sometimes they will ask you a question, write the general electronic configuration for S block elements. General electronic configuration, when they ask, you have to mention noble gas configuration. Along with this NS122, you have to mention in a bracket noble gas. It means noble gas configuration into NS122. But if they ask you a question, what is the outer electronic configuration, you will write only NS122. Clear? Now, that was about S block elements. So, all the metals here are mostly, they are metals itself. That is why we call alkali metals and alkaline earth metals. And here one more point that you need to remember is the one which is here, cesium and francium. They have very low melting point. That means they melt faster. So that's about S block elements. Hope no confusions there. Then you have to note down the points that I have mentioned. Next, let us move on to P block elements. Under P block elements, you see group 13 to group 18 comes under P block elements. The reason is because the last electrons will enter P orbital, and so they are classified as P block elements, or they are called as P block elements. So let me mention here the points related to P block elements. What is it? P block elements starts from group 13 to group 18. However, for the general trend when we study, we do not consider group 18 for most of the cases because they are called as noble gases. Why they are called as noble gases? You know the reason. They are called as zero group elements, or they are called noble gases or inert gases. The reason is because they show least reactivity. They do not react easily. That will be your reason that you need to mention if the question is asked based on noble gases. Next, we will see group 13 to group 17. Yes? Or say group 13 to group 18 together, you call them as P block elements. So we will see that here the outer shell electronic configuration, the way you mention is NS2 NP. Outer shell electronic configuration will be NS2 NP126. This is for whole P block elements. The outer shell configuration is given. What is it? NS2, because already S orbitals will be filled. Here in case of S block elements, you have seen NS2, so 2 electrons will be filled here in the S orbital, and here the electrons goes on entering in P orbital. So 1 to 6 means, see here, this is group 13. In this NP1, NP2, NP3, group 16, NP4, group 17, NP5, group 18, NP6, completely filled in P. 6 electrons, noble gases. So here let me tell you, for boron the outer shell configuration will be 2p1, that is 2s to 2p1, here 2s to 2p2, 2s to 2p3, 2s to 2p4 for oxygen, fluorine 2s to 2p5, like that it goes. Hope it is clear now. So generally the outer shell electronic configuration we write as NS2 NP126. Whereas if they ask you general electronic configuration, how do you write? You'll have to mention noble gas configuration into NS2 NP126. Clear? Now let me tell you one more important point, that S block elements and P block elements from 13 to 18 as well as 1 and 2 together, they are called as representative elements. What are they called as? S block, S and P block elements are called as, together called as representative elements. The reason can be that these elements are most commonly involved in most of the chemical reactions and they are called as representative elements. Group S and group P together. S block and P block together, they are called as representative elements. So that's about P block elements, the important points that you need to remember. Next, when I speak about some properties, I'll again come back to these elements. Now, next we will see what are D block elements. See, D block element starts from group 3 to group 12. These are the things you need to remember. Very important. So group, that is D block elements, starts from group D block elements, group 3 to 12. Group 3 to group 12 elements are called as D block elements. Now, why are they called as D block elements? They are called as D block elements because the valence electrons, valence electrons means the electrons available for bonding or reactions. They enter the d orbital, and that too you must mention penultimate d orbital. Penultimate means one before the last one. Ultimate means last. Penultimate means before that. See, here scandium 21. You write 3d1 4s2. Here titanium 3d2 4s2. Vanadium 3d3 4s2. 3d5 4s1. Chromium, however, it shows exception, isn't it? Manganese 3d5 4s2. Iron 3d6 4s2. Cobalt 3d7 4s2. Nickel, again copper, again it shows exception, 3d10 4s1. And then zinc. In zinc, 3d10 4s2, all the orbitals are completely filled. These elements in D block are also called as transition elements. D block elements are also called as transition elements. Why they are called as transition elements is because why D block elements are called as transition elements is because they act as a bridge between S block and P block. Because there is a bridging between S block and P block elements, S block and P block elements, we call these as transition elements. Clear? The reason is because they act as a bridge. Now, what is the electronic configuration for D block elements? It is outer shell configuration is n-1 D 1 to 10 ns 1 to, that is ns 0 to 2. This is the outer shell electronic configuration. It is n-1 D 1 to 10 ns 0 to 2. The electronic configurations are again important. They can ask you questions based on that again. And here that means D can be varying from 1 to 10. That means in D orbital 10 electrons can be filled. If you see here in this case D1 D1. Even the continuation of this is here 5d1, then continuation of this is here actinium 6d1, 3d2, 4d2, 5d2, 6d2, like that it goes. And D can be 1 to 10. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. D shell will be filled. Whereas 4s can be, that is ns can be 0 to 2. It can be 0 or it can be 2 also. That's about D block elements. Now again, general, if they ask you, you have to mention noble gas and then mention this one. Hope I'm getting the things clarified to you. So here you must see zinc, cadmium and mercury. See, this comes under group 12. Zinc, cadmium, mercury. What can be the special property? They are showing some similarity, isn't it? What is the similarity there? The similarity is, see, the D orbital is completely filled in all these 3d10, 4s2. In D, 5 orbitals will be there, isn't it? 1, 2, 3, 4, 5. Maximum how many electrons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maximum 10 electrons can occupy. In zinc, 3d10, 4s2. Cadmium 4d10 5s2, mercury 5d10 6s1. See, 6s2. See here, since they have completely filled electronic configuration, they do not show most of the properties as that of other transition elements. You can't say that all the properties that are shown by other elements can be shown by zinc, cadmium and mercury. Remember that exception: zinc, cadmium and mercury. Mercury is Hg. They do not show all the properties of transition elements or transition metals. These are metals, these are all metals. D block, S block, F block are all metals. Whereas in P block we have most of the non-metals. We will speak about it. Now D block is clear. Let's see the speciality of F block elements now. Hope you are making points of it. If not, please do make. F block elements. See, F block. F block elements are placed in a horizontal way than in vertical ways as that of other blocks. The reason is because these show similarity in a horizontal manner than in vertical manner. Usually here how the things goes, lithium, sodium, potassium, rubidium, they show similar properties. Again, beryllium, magnesium, calcium, strontium, barium, they show similar properties. These are all showing similar properties, means same kind of properties downwards. Whereas here, see, it starts from 57 to 71 and then again 89 to 103. That means usually we say 58 to 71 and 90 to 103. These elements shows horizontal similarity. Like this they show similarity. That is why they are placed separately and are called as F block elements. The reason why they are called as F block elements because the valence electrons enter F shell. If you observe for cerium here 4f2 6s2. For uranium 5f3 6d1 7s2. F orbital gets filled there. The electrons enter F orbitals and that is why they come under F block elements. Let us write the general outer shell electronic configuration. The outer shell electronic configuration is written as n-2 F1 to 14. So the possibilities are the electrons in F orbitals can be 1 to 14. n-1 d. So here the d orbitals can be from 0 to 1 and then here I'll write ns2. This is the outer shell electronic configuration for F block elements. What is the name for F block elements? Do you know? These D block are called transition elements. Here F block elements are called inner transition elements. They are called as inner transition elements. And the elements, one more point under this is the elements after uranium. After uranium, you remember here neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium, lawrencium. All these are called after uranium. The elements are called as trans-uranium elements. What are they called as? Trans-uranium elements. Elements after uranium are called trans-uranium elements. These were the general introduction for S block, P block, D block and F block elements which you need to understand in order to go with the further more concepts. Next, let me explain about the metallic and non-metallic properties. It's again very easy. Metals, non-metals. When we say what are metals, we say metals are those which is malleable and ductile. Do you know what is malleable and ductile nature? Malleable and ductile. If the elements are malleable and ductile, we call them as metals, we say, and they have shining property, or they are lustrous. Lustrous means they have a shining surface, and they are good conductors of heat and electricity. These are all the things which we note under metals. Yes. Malleable, ductile. Malleable means you can convert the substance, say the element, into the form of sheet. Thin sheet you can make. You can beat it and you can convert it into thin sheets. Ductility again means you can convert it in the form of wires. Say copper, you can form it a wire. Iron, you can beat into sheets. All those. So malleability and ductility are again the important properties of metals. Now in the periodic table, which are metals, which are non-metals? Left hand side, as I have told you, group 1, group 2, all are metals. So here lithium, sodium, potassium, rubidium, cesium, francium, beryllium, magnesium, calcium, up to radium. Radium is radioactive, and even francium is also radioactive element. You know what is radioactivity again? So these are all metals, and I have told you D block elements are all metals. So that means left hand side of the periodic table mostly has metals, means most of the metals are seen in the left hand side of the left hand side of the periodic table. As you move to the right side of the periodic table, you see here boron, carbon, nitrogen, oxygen, fluorine. What are these? They are non-metals. Then as you come down, you see tin, lead, antimony, bismuth, tellurium, polonium. So polonium is radioactive, however. These downwards, as you move down, you see most of the metals. Here, non-metal nature. So what is it? Left hand side are all metals. Even this also, F block also. As you move to the right hand side, here above are non-metallic nature and down are metals. So here if you observe, above you have non-metals and below you have most of them are metals. And there are some substances like silicon, gallium, germanium. There are some special properties. So now hope it is clear. Metals on the left hand side, non-metals on the right hand side. And the two between metals and non-metals, there is one more called as semi-metals. What do we call them as? Semi-metals. Or we also call them as metalloids. Metalloids. So what are metalloids? Metalloids are those which shows properties in between that of metal and a non-metal. And here the special thing is, say silicon, germanium, gallium. These are all example for silicon, germanium, gallium are examples for semi-metals or metalloids. Hope this thing is clear in case of metals and non-metals as well as semi-metals. Now next we shall see the general periodic trends of these elements. Just have a look at it. I will explain what it is actually. See, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. As you move from left to right, what happens to the atomic radius or atomic size? Lithium will have a smaller size. Beryllium, still smaller size. Boron, again smaller, you can see. The reason I will explain why. And what is atomic radius again? We shall understand about it. So now it's not easy to explain the size of an atom. Atomic radius. Now from here onwards, whatever you are studying, these are the properties of these elements, periodic trends we are going to study. The other part was the general introduction that we have studied. Here onwards we will be studying the periodic trends. That means how the properties varies, or what are the very important properties. Atomic radius. So before telling what is atomic radius, let me tell you, it is not easy to explain the atomic radius. That means experimentally it's difficult to determine the radius of an atom, because if you remember, when we studied the model of atom, we said that the size is very small of that of atom. It is, the radius of atom is about 10 to the power minus 10 meter. You remember? Approximately equal to 10 to the power minus 10 meter, we said. So when we say the topic of atomic radius, usually what they do is, directly we don't have any method, isn't it? So they find covalent radius. Covalent radius means what, you know? If two atoms are bonded, say for example Cl2. Cl2 means chlorine. It is a molecule now. Why it is a molecule? Two chlorine atoms combine together and they form chlorine molecule. So to find out the radius, what they do, this is one atom now, this is one more atom. So they have a bond in between. Bond in between in the sense, the force of attraction, we say how much is the force of attraction. Based on that we say there is a bond in between. So they calculate the bond distance or bond length, how it is from the center of one atom to the center of the other atom when it is bonded. Then they find out the distance, internuclear distance we say. Inter means between, nuclear means related to nucleus. Here atom will have nucleus. So that internuclear distance will be taken if the distance, internuclear distance between the two covalently bonded means by sharing of electrons. This will give one electron, this will give one electron. So bonding takes place. So between covalently bonded atoms, we find out the internuclear distance, and half of it if you take, you get the radius of it, isn't it? So this is covalent radius. In case of metals, we call it as metallic radius. So metallic radius is, you know, metal which is positively charged will be surrounded by kernel of electrons. Now if there is one more metal, again it will be surrounded by kernel of electrons. So these two, when they are bonded, they find the half of internuclear distance, same. But in case of metal, we call them as metallic radius. Together about covalent radius and metallic radius is discussed in this particular unit as atomic radius. So how do you define atomic radius? Atomic radius is defined as the distance between the center of the half of the distance between the centers of the nucleus of the two atoms. Or if simply you can say atomic radius means radius of an atom. So I have told you experimentally it's difficult to determine directly of what is the radius. So some spectroscopic methods will be used, or X-rays will be used to study the size of an atom. Now what is important is you should know how it varies across the period and down the group. Across the period means like this, in the periodic table, this way, in this manner, across the period, and down the group, when I say, it means in a group how it varies. Remember, this is a common way I explain it to the students. They say it seems easier if I explain this way, and so I'll explain in the same way to you also, that here the size of atom across the period goes on decreasing. What happens? It goes on decreasing. Understand it properly so that it will be very easy to understand other concept. Whereas as you move down the group, the size of atoms goes on increasing. Size of the atom goes on increasing. I'll tell you what is the reason here. the size goes on decreasing, atomic radius goes on decreasing across the period. That means compared to one element, the next element will have smaller size. Again next element smaller, the size goes on decreasing.